Welcome to lecture 19. So we'll outline the construction of p-adic numbers QP. So on Q we define this p-adic absolute value, and QP is defined to be the completion of Q with respect to this p-adic absolute value. And so many of you might have seen the construction of R. Construction of real numbers is given as the completion of Q with respect to the Archimedean absolute value. And again, somehow the point is that in both these cases Q is not complete. There are Cauchy sequences that don't converge with respect to the p-adic absolute value, similar to how it's not complete with respect to the Archimedean absolute value. So the construction is almost identical, so I'll only outline the main steps. So we'll only outline the main ideas and steps. Of what it means to complete Q with respect to the p-adic absolute value. So the first thing is you have to form a set of all Cauchy sequences AN in Q. So that is, you take all sequences such that the sequence is a Cauchy sequence. And again, when I say Cauchy sequence, it's with respect to the p-adic absolute value. And step 2 is to show that this set is in fact a ring with respect to component wise addition and multiplication. That is, if you have two sequences that are Cauchy, then in the sum you can form a new sequence given by the sum, and another new sequence given by the product, and you have to show that this new sequences are also a Cauchy sequence in Q. So we've almost done this. So this is, you have to use proposition 42 and 46 from the earlier lectures. Okay, and so the constant sequence where each term is 0, that's the additive identity. You see, and the constant sequence where each term of the sequence is 1, that's the multiplicative identity. Okay, and the next step is you just extend the function this p-adic absolute value on C as follows. You know, if you have a Cauchy sequence, it could be a null sequence, And if it's a null sequence, you just set the p-adic absolute value of that sequence to be 0. But otherwise, if it's not a null sequence, so if you have a Cauchy sequence that is not a null sequence, now use lemma 43 to find an n naught such that the absolute value of a n eventually just matches up with the absolute value of this a n naught for all n larger than n naught. And for these sequences, which are Cauchy but not null, you define the absolute value, the p-adic absolute value of these sequences to be, you take a n naught and just look at the p-adic absolute value of that. Okay, so this is what you do if sequence a n is Cauchy but not null. Okay, and the idea really is that this new function on C, this also induces a topology on C, and addition and multiplication are continuous with respect to this metric topology, this topology, induced topology. Okay. So we have a ring and you can form an ideal. So you look at the set of all null sequences in C, and so we already know that every null sequence is Cauchy. And what you have to show is that this sequence, this set of all null sequences, this forms an ideal of C. And just an observation that the constant sequence a n equals 1 is not in n, so n is in fact a proper ideal of C. Okay, so you have a ring C. It's not hard to show that it's commutative because the way we define multiplication is product-wise multiplication. We have a ring, we have an ideal, and so you form the quotient ring, which actually turns out to be a topological ring, the C mod n, and by construction, because we are using all Cauchy sequences, by construction this ring is complete with respect to the topology induced by this p-adic absolute value function. Okay, and QP is defined to be this ring C mod n. Okay, and so the main point is to show that this quotient ring is in fact a field, is to show that C mod n is a field. Okay, and so what does that mean? So what you have to show is that the ideal that you are quotienting out by, that's a maximal ideal. So what we have to show is that n is a maximal ideal of C. Okay. So suppose not, then there exists a Cauchy sequence, say an, that is not a null sequence, such that, you know, when you look at, say, J is the smallest ideal generated by, say, an, the sequence an and n. So this ideal J is not equal, it's a proper ideal, so let's just say it's a proper ideal of C, that is, J is not the whole of C. Okay, so suppose for the sake of contradiction that n is not a maximal ideal, you've got this element, this Cauchy sequence an that is not a null sequence, with the property that if you look at the ideal generated by n and this non-null sequence, you get a proper ideal. Okay, since this an, the sequence an is a Cauchy sequence that is not null, you again apply lemma 43, you get an n naught such that eventually when you take the p-adic absolute value, that matches with the p-adic absolute value of an naught, and that's not 0. This is true for all n larger than n naught. Okay, we also observe that inversion takes Cauchy sequences to Cauchy sequences. So using these observations, define a new Cauchy sequence given by Bn, which has the property that is just 0 if the index is less than n naught, and if the index n is larger than or equal to n naught, you take it as 1 over an. Okay. None of these an can be 0 because by lemma 43 we observe that its p-adic absolute value is not 0, and the fact that this is Cauchy relies on the fact that the sequence an is Cauchy, and the property of being Cauchy is a limiting property. It only depends on how the sequence converges eventually, and we just saw that inversion takes Cauchy sequences to Cauchy sequences. So beyond this n naught, I've just inverted an. Okay, so now form a new sequence which is also Cauchy given by Cn, which is say Bn times an. Okay, and since Bn is 0 if little n is less than n naught, so initially it's just 0, but if little n is larger than equal to n naught, you see that Bn is 1 over an, and the product of an and 1 over an is just 1. Okay, so and again observe that the sequence Cn is just this product of the sequence Bn and an. By construction, this sequence given by ans is in J, the sequence given by Bn is Cauchy, so it belongs to C. So this product in fact belongs to J, since J is an ideal. And now form this new sequence, say Dn, which has the property that it's 1. So I'm just going to invert this property of Cn. So it's 1 if little n is less than n naught, and it's 0 if little n is larger than or equal to n naught. And again observe that the sequence Dn is Cauchy, and in fact it's null. Since for all little n larger than n naught, so eventually Dn is just 0. So eventually it's 0 on the nose. So the limit as n goes to infinity of Dn is just 0. So thus the sequence Dn belongs to the ideal generated by all the null sequences. It's in n, and the ideal n is in fact inside J. So on the one hand we have a sequence in J, and we also have this other sequence Cn in J, and since J is an ideal, the new sequence given by the sum of Cn and Dn, that will also be in J. But what is this sequence? What's Cn plus Dn if little n is less than n naught, it's 0 plus 1, and if little n is larger than n naught, it's 1 plus 0. So in both cases it's 1 if little n is less than n naught, and if little n is larger than or equal to n naught. But this is the unit element. In C. So in fact J is not the proper ideal. So the only possibility is that this ideal given by the null sequences, this is a maximal ideal of C. Okay, so this completes the proof of the proposition. Okay. Thank you.